All right, so our next presenter is Kody Kantor from Join, and I believe we're going to be talking about ZFS capacity calculation. So please welcome Kody.
Thank you. Yeah, so my name is Kody Kantor. I work at Join. I've been there for like 2.5 years. And this talk is about something that I wrote that will generate Visio diagrams for you. I'm just kidding. Yeah, so I think probably a lot of us have had to answer some questions when capacity planning comes around. If you folks are like buying servers and stuff. And with ZFS, the answer to these questions is actually really complicated. Usually somebody just says, like, hey, like, where's all of our storage going or something? And as somebody who knows something about ZFS, you have to like sort of explain all these little nuances of ZFS, and it can be really difficult to express these things to folks that maybe aren't as interested in ZFS or just want to answer their capacity planning calculation. So like some of these things like record size stripe with compression, like how do they actually impact the data that we need to store in production? So there's a few ways that we can like, well, I guess the impetus to this talk is really the record size portion of this. Like at Joint, both in the community, like in community interactions and internally, there's a lot of questions about what this record size setting is. You know, we talked about a little bit already today, but like, what does it do? We know that it can probably affect performance, but can it also affect the capacity of usable space on our pool? So that was really like one of the things that one of the reasons that we started doing this work in modeling ZFS capacity. So the first, like, I don't know if you would say like the naive solution to like modeling out capacity usage is just to like use production hardware, write production data to it, and see like how much space is used by that. The problem with this is that it's like really expensive to get these like production size machines, you know, hundreds of terabytes of storage. You can't just like, you know, take that out of your pocket and start using it. And then you need access to production data. Like, is your customer going to be okay, like having you just copy data from production into this like other machine that you have to do some analysis? And then also it's super boring. Like, I don't know if you guys have had to do this sort of stuff, like filling up a 200, like 300 terabyte pool takes forever. And like usually if you want to make it not super boring, you have to write a bunch of software to do this anyways. Which, I mean, I like writing software, but like if I'm going to write software, I don't want to like, I would rather like do more interesting things. So we sort of came up with this option B where we actually have no time or hardware. So this is probably the reality for most of us. And what we ended up doing was gathering like statistics about our production data and then sending it through a script. And this script you can just run on your laptop. So this is perfect because we all have like a little laptop or something. So there are also problems with this, and that's what this talk is really about. It's about all the problems that we ran into when we were doing this modeling, and the problems really continue. Software is really hard to get right, and modeling something like ZFS is really difficult. It's a very complex system. The other tough part about this is that we have to go in this knowing that we're doing this for capacity planning decisions. So any mistake that we make along the way could be a huge mistake down the line. Like if you buy too few machines, then like you have to, what do? Do you like tell your customers, oh, there's no more storage? Or do you buy too many machines and make your cost per gigabyte not as attractive as it could have been? So I guess like the initial theory here when the impetus was record size setting. So the initial theory and understanding of like my understanding was that the capacity usage for parity data in a RAID-Z like pool topology doesn't change as block size changes. So like my thought was, hey, if you write like example 1 here, you write you use a 1 meg record size and you write a single 1 meg file, then it'll just be like 1 megabyte plus whatever parity data, RAID-Z to like 2 disk sectors of AK. And that's only 120, like 1/128th of the like file size and overhead. But if you use like 128K records, like the RAID-Z would be so much more because you have more records. Turns out this assumption is incorrect, but I didn't know this at the time. That's why it's an assumption. So we went along with it anyway. And like the first thing we did was try to verify like that ZFS was like doing the things that we thought it was doing. So here we just like created a file system and set its record size to 1 meg, and then we write a 1 meg file uncompressed, and we can see that on the disk it is 1 meg, taking up 1 meg. So that's good. That's exactly what we wanted. But then if we write 1 more byte to that same uncompressed file in its uncompressed file system, suddenly the size on disk becomes 2 meg. So even though we're storing 1 meg plus 1 byte of user data, it looks like we're storing, well, we are taking 2 meg of space on disk. And that's not good. That's like 50% efficiency. You went to having like really good efficiency of storing 1 meg exactly to taking 2 megs to store effectively 1 meg of data. So that was like really scary. You know, the last record wasn't truncated. And this is when we sort of realized that this isn't like a trivial thing anymore. We can't just like do easy multiplication. We have to take into account the object size and how it can influence the efficiency of the data that we're storing. So we have to consult the file size distribution of the files in our pool. So this is an eye chart. The y-axis here is the number of objects on a pool. This is just like some random pool that I took out of a like Jenkins service in our staging environment. And then the x-axis here is object size in megabyte buckets. So on the far right there is 10 meg, and then on the left here is like in between 0 and 1 meg. So you can see that we have a ton of really tiny files, a ton of files less than 1 meg. So I mean, like the big problem with this is that files are millions and millions, or pools are millions and millions of files. How are we going to model that? We can try and shove it in like a Google Docs spreadsheet, which is totally what I tried to do. But I guess like Google Docs doesn't like ingesting like a paste buffer of 2.5 gigabytes. You know, I very quickly learned that Google Chrome just can't handle that sort of thing. So what we did is we created this simulator. And initially the simulator was going to be really trivial. It's just like figure out how much user data you have, add this parity because it's constant, like, you know, it doesn't change. And then we get this nice little output on the right here, which I'm sure you can shove in a Visio diagram if you need to, I don't know. And with that data we can draw, like we drew this fancy graph here. You see on the bottom, the blue section is like user data, that's constant. But then with the simulator, we could dynamically change the record size that we were modeling with. So, you know, the first run was 128K, just the default, but we could also simulate how much capacity would be used if we used a 1 meg record size. And that red section is the wasted space. So, like, since we were still under the assumption that the last record in a file, if it goes over record size, would be a full record, that space was, like, tallied as wasted. And then RAID-Z capacity, like if you look at this is totally wrong. This is not accurate based on like the assumptions that we had taken previously. So we sent that out to the company, and you know, I was talking to Dave Pacheco, somebody at Joyent. I used the scope with permission. He's like, yeah, I wonder what would happen if you used compression on the data set. I was like, yeah, that's like a really freaking good question. I don't know why I didn't do that. So like, turns out that if you like actually use compression, then that last block problem that takes up an entire record, that's not a problem anymore. Like it still uses a little bit more space. Like it's not exactly 1 extra byte of capacity used, but it's much, much less than an entire megabyte record. So like now I sort of thought, okay, well I was totally wrong about like a lot of my initial assumptions here. So let's do a bunch more research on how ZFS actually works. So, you know, read blog posts, like Matt's blog post on like how I learned to love RAID-Z. We had some blog posts to join internally. You read a bunch of code, look at ZDB again, look at the source code for ZDB, because otherwise you don't know how to use ZDB, I guess. And we learned that we need to take into account all these other things, like the parity complexities padding, which I think Alan was asking about. How wide is your stripe? We weren't even taking into account stripe width in our capacity calculation in the first version of the simulator. Like block pointers sometimes take up a non-trivial amount of space. minuscule allocations behave differently than really big allocations. And then, of course, compression, which is can be really important as well. So we iterated on the simulator, and now we get a little bit more granular output. This is for one of the later versions of the simulator, where we can see where our storage is actually going. And using this, we can make a lot more accurate graphs. So on the top left here, this is similar to that first graph that I showed. You can see the blue is user data, RAIDZ is the gray, and in the middle there is all this other stuff, like padding, block pointers, and this takes into account smaller allocations and compression. But other things that we can do is actually figure out how many blocks we're allocating, because that can make a difference in the performance of other things in the system, like scrub resilver, as well as maybe fix some compression problems that you have. And then stripe width, if you want to optimize for padding for whatever reason, you can see as stripe width changes, how much padding are you going to have in the system. So to generate the data for a pool that has, I don't know, 60 million files in it, it takes 3 minutes. So this is I would much rather do something that takes 3 minutes than fill up an entire 300 terabyte pool. And I think you guys probably would too. So I guess that's really the simulator in a nutshell. The problem with it is that it is software that's separate from ZFS. So it's only going to be as good as the knowledge of the person that implements it. So in my case, I know that there's still a bunch of problems in the simulator that really should be fixed to give us better insights into capacity usage, like pool usage. This only takes into account the file allocation stuff, but I know there's a lot of overhead in the pool, pool-wide slop space, per pool capacity usage, ZAP. If you guys are using large D nodes and putting a bunch of stuff in there, this doesn't account for that. So the simulator could be improved. There's also this null pool idea that I was sort of just spitballing, where you write data to a pool, except the data isn't actually written, just whatever minimal amount of data is required to make the pool work. So then you can sort of model ZFS without actually having to write a lot of data. Might be faster, but you would need some hardware too. Yeah, so I think that's mostly what I have. I mean, I have some links here if folks are curious. The simulator, it looks like this link was clicked, which is cool. The simulator is the third thing on the bottom. It's actually just an awk script. It's 400 lines or something, and awk isn't the most performant thing ever, but it's sort of fun to write. So yeah, if you're interested, we can iterate on it there. Really, it does need a better place. And here's some other resources for blog posts that, if you're curious about how ZFS allocation works. Yeah, so if folks have any questions, I think we have a little time. Yes, Paul.
You were saying that really the only way to understand ZDB is to read the ZDB source code, and I think that you're probably not. You, as somebody who is learning to use it, do you have suggestions on ways that we could make it more usable and less complicated?
Yeah, so the question is ZDB, Paul sort of confirms that he thinks that it will be difficult to understand ZDB without reading the code, and he asks if there's any way that we can make it better. I mean, ZDB's man page is sort of frustrating because it just says yeah, add more of this letter for more things. It's really unclear. And also the fields that are output in ZDB, I think that they make a lot of sense if you're in the ZFS code a lot. But as somebody that's just casually observing a system, they're not documented really anywhere unless you source dive. And even when you source dive into ZDB, then you have to go into the ZFS core code and figure out in this struct, this is what this means, and look at where it's used. So I don't know. I mean, more documentation, I suppose, or maybe other output formats would be helpful as well. Because right now it's sort of just a big raw data dump. But maybe that's what it's useful for. I'm not sure. Yeah, Steve. Yeah, absolutely. So the question, so Steve asked, the data, it took 1 point, when we enable compression on this file, previously it took 2 meg to store 1 meg and 1 byte. after we enable compression, even though it was incompressible, because it was incompressible, it was from dev random, we still saw benefits of compression. And yeah, like absolutely, like you just turn compression on, even if you have incompressible data for the cases like this, I think. And our data, for the most part, is mostly uncompressible. Yeah.
The trick that you showed that pretty much like ZFS is going to the RAID padding or like the A-shift roundup or other like obscure ZFS stuff had a big impact.
Yeah. So the question was, the data that we showed, like it's mostly like predictable for the data that we're testing with. But have we tried with any other data sets that might tickle other pieces of ZFS, like using a lot of padding or having more RAID-Z overhead? And yes, last night actually in the hotel, I was just thinking like, hey, what if we use like really, really tiny blocks on like a RAID-Z2 pool? And you could see that like the data was like 100 gig of data was on the pool, like user data. But then there was another 50 gig used for padding, another 50 gig for RAID-Z over parity data. So yeah, like you can model all sorts of stuff like this, even if it's just for fun. And it's really cool to see how that can change things. Yep. Yeah, you probably could. So what I use, I just like ran a find on some like pool directory. So you could run that on like find on the root and throw that into the simulator and get an output. So that's basically what I was doing. You could totally do that on like a live production data set. Yeah, or you could do it offline on a different machine like I did. Yep. Alan? Yeah. So Alan says that he's also seen some differences from like the data that I presented, data that he's seen. So it'll be interesting to run that through the simulator as well. And yeah, I totally think so. And there could be inaccuracies in the simulator too, just because we don't understand or we haven't modeled it perfectly correct. Yeah, I would say like for us, like at Joyent, even small percentage gains, even if it's like a 1% gain in efficiency, is huge when you like make it to a really large scale. So this stuff, even little tiny things, is important for us as well. Yep, right here.
Are you familiar with the MDB macro for ZFS block size?
I'm not familiar with it. Does it give you some granular information about like DVAs and stuff?
It gives you a breakdown for all the different types of data and how much space.
Cool. Yeah. So it sounds like is it : block stat, BLK stat? Yeah, : BLK stat and MDB will, I guess, give you a lot of statistics, like pool-wide statistics about how much capacity is being used by different things in this. Yeah. Yeah. So Matt says it's similar to like ZDB dash as many B's as you can fit on a line. Yeah. So the thought is that if we can produce similar output using the simulator and the output of ZDB minus B infinite or block stat, then yeah, we could like sort of cross-check the algorithms. Yeah, I agree. Cool. Yeah. Well, thank you very much.